Hi, here I have an inductor of 100 microhenry, and here I have a very similar inductor, but the inductance is 3.3 microhenry. So my first question is how we know the inductance that we require for our buck converter. And I have another question. As I said, here I have 100 microhenries, but here I also have 100 microhenries. Why the size is so different in these inductors? So in order to answer these questions, we need to study the current waveform we have through the inductor of a buck converter. So this is the target for this video. Okay, so let's try to get the current waveform. First of all, we have to consider some points that are very similar to those that we already considered in the previous video. First, we will consider ideal components, so power losses in our circuit are zero. Second, we consider that our buck converter has achieved steady state conditions, so waveforms are periodic, average current through the capacitors is zero, and average voltage across inductors is zero. Third condition is the capacitance of our capacitor is very large. It means that the voltage ripple across the capacitor is zero, and we consider as a consequence that the voltage across capacitor is constant. And the last point is different to the previous video. In the previous video, we said that inductance is a very high value. As a result, current ripple through the inductor was zero, and we considered that the current through inductors were constant. In this video is different. Our target is to determine the shape of that current, the waveform that we have in the current through the inductor. So we will consider that our inductance is not infinite. In this way, we want to know why we have this kind of current waveform in our inductor. The target is to demonstrate why we have this shape. We want to determine the average value of that current, and we want to determine the peak-to-peak current ripple. The only limitation of our analysis is that we are going to consider that the current through the inductor is always positive. What happens if we reach 0 amps is something that we are going to address in another video. Okay, so let's start with the analysis. First of all, we are going to determine the average value of the inductor current, and we are going to apply Kirchhoff current law in this node. Here we have the inductor current, the capacitor current, and the output current. If we apply Kirchhoff current law, we can say that the inductor current is the output current plus the capacitor current. But we want the average value. So we put it in this way. And now we will take into account a property of the average value. If we do the average value of the sum of two waveforms, x1 and x2, we can apply the general definition. Is this one. But if we apply a property of integrals, that is, we can split the integral in two parts, we have this expression, where we have the integral of x1 and the integral of x2. In this way, what we have demonstrated is that the average value of a sum of waveforms is the average value of the first waveform plus the average value of the second waveform. So we are going to apply this idea in our case, and we can say that this is average value of the output current plus average value of the capacitor current. And now we are going to take into account something that we already explained in the previous video. The output current is VO over the output resistor, the resistor that models the load and that we connect at the output. Both values are constant. VO is constant, R is constant. So the output current is constant, capital I-O. In this way, we can say that the average value of I-O is directly I-O. And the second point is that since we are in steady state conditions, the average current through a capacitor is zero. So the average current through the output capacitor of our buck converter is zero. In this way, the average current through the inductor of a buck converter is the load current, the output current. Okay, so until now, we know the average current that we have through our inductor, but we don't know, let's say, the shape of the waveform. That is our next target. In order to answer that point, or in order to answer that question, what we need to take into account is the voltage that we apply to the inductor. This is something that we already studied in our previous video. We obtained that, or we said that the voltage across the inductor can be studied in two states. In state 1, the voltage is the input voltage minus the output voltage, and in state 2 of the switching period is minus VO. Remember, in state 1, we turn on our switch A, and we turn off switch B. As a result, VL, the voltage across the inductor, was VI minus VO. VI minus VO. And we keep this scenario from time equal to 0 to D switch. D is the duty cycle, T switch is the switching period. And remember, in state number 2, we turn off switch A and we turn on switch B. As a result, the voltage across the inductor is minus VO. This is the situation that we have here. So after we remember that, we can determine or try to determine the shape of the inductor current. In order to do that, we need to consider the general expression of the inductor current as a function of the voltage. Remember, we have an initial value of the inductor current plus 1 over the inductance integral from the initial instant of the voltage across the inductor. Well, we will take into account another point, and that point is if we do the integral of a constant value over time, what we get is a line, okay? This is the situation that we have if we consider the two states of our converter, because in state 1 we apply the voltage that we apply across the inductor is VI minus VO, constant voltage, and in state 2 we apply minus VO, another constant voltage. So let's put that here. In state 1, VL is VI minus VO, is a positive constant value. In state 2, VL is minus VO, is a negative constant value. Remember, VI is higher than VO. VO is a positive value, so minus VO is a negative value. Okay, so if we take that into account, it means that in state number 1, we have the integral of a positive constant value. We will get line with a positive slope. In the second state, we have the integral of a negative constant value. We will have a line with a negative slope. Let's try to draw it. Initially, we have an initial current value that we don't know. Let's consider that we start here. And in state number 1, we have a line with a positive slope. Let's consider that we have this. In the second state, we have a line with a negative slope, but, well, we don't know where we have to finish. No, yes, we know where to finish, because if you remember, we are in a steady state. Our waveforms are periodic, so we have to take into account that the current at the end of the period must be equal to the current at the beginning of the period. So we know where we have to finish. We have to finish in this level, okay? So we will have something like this. Now we know that the shape of our current through the inductor is like a triangular waveform. And we finish at the same point that we have at the beginning of the period. Well, let's highlight some important parameters of this current waveform. I think that we should highlight the minimum current through the inductor. We should highlight the maximum current through the inductor. And in the middle, we have the average value. Okay, we already know that the average value is the output current. And another thing that I want to highlight is the peak-to-peak current ripple. Well, before we continue, let me point out one thing. If we know the average value and if we know the peak-to-peak current ripple, we know everything about the current through the inductor, because the maximum current can be expressed in this way. And the minimum current can be expressed in this way. So, we already know the average value of the current through the inductor. Let's evaluate the expression of the peak-to-peak current ripple. So let me remove everything I have here. In order to evaluate the peak-to-peak current ripple, we will also consider the general expression of the inductor current we have at the top of the slide. Because basically, we can say that inductor current ripple is the maximum value minus the minimum value. But at the same time, we can express this in a different way. We can say that the maximum value is the current that we have through the inductor when T is equal to D times T switch, and the minimum value is the inductor current at T equal to 0. So I will try to express this term as a function of this term. I will use this general expression. We can say that this is IL at T equal to 0 plus 1 over the inductance. I will do the integral from 0 to the end of state number 1. And I have to consider the voltage that I have in state number 1, Vi minus Vo. And now I have to put the second term. So I put minus the initial current. So in this way I can simplify the expression, and now I only have to do the integral. The answer is 1 over the inductance times Vi minus Vo times the switch. And I will manipulate a little bit the final expression because I prefer to consider switching frequency instead of switching period. So I will take into account that the switching period is 1 over the switching frequency. And I will express the output voltage as a function of the duty cycle and the input voltage. We already know that expression from the previous video. If we consider that, the expression of the peak-to-peak current ripple is this. So, as we can see here, the peak-to-peak current ripple depends on the voltage conversion that we do, because it depends on the duty cycle and on the input voltage. And it also depends on the inductance of our back converter and depends on the switching frequency. Well, so what we are going to do now is to evaluate the impact of different operating conditions on our current waveform. First of all, we are going to evaluate what is the impact of increasing the output power. Let's consider that we have this current through the inductor where we have this switching period, we have this average value, the load current, and we have this peak-to-peak current ripple. And we want to know what happens if we increase the output power of our converter. Note that here I have the expressions of the peak-to-peak current ripple and the average current through the inductor to support this explanation. So what happens if we increase the output power? The output power is the output voltage times the output current. When we supply a load, we don't change the voltage supply. The load will require a fixed voltage and we have to preserve it during all the time. So that load will consume more or less power depending on the things that load is doing. Imagine that you have a microprocessor, you have to supply it with perhaps 3.3 volts, and it will demand more or less current depending on the different task it has to do. So basically, if we increase the output power, what we do, or the effect, is that the output current will rise. The output voltage is the same. In terms of the circuit that we use, it will be translated into reducing the load, the resistance that we consider at the output. The load, actually, we say that is higher. Okay, but in summary, if the output power rises, it means that the output current will rise. The resistance will fall, and we have the same voltage. What is the impact on the inductor current? If we check the expressions of this inductor current ripple and this average value, what we see is that the impact is on the average value. We don't have any modification here in the peak-to-peak current ripple. So as a result, what we see is something like this. The waveform goes up, but the shape is the same. The peak-to-peak value is the same. The difference is in the average value. Second point, what happens if we have a buck converter and we have, let's consider this initial condition with some period, some peak-to-peak value, some average value, and now we want to change the inductance of our buck converter. We want to increase it. If we check these expressions, we see that the impact is here. What we see is that the inductance is in the denominator of the peak-to-peak current ripple. So if we increase the inductance, the peak-to-peak current ripple falls, as we can see here. Note that this is the initial current ripple and this is the final current ripple. As you can see, the period is the same. The difference is in the slope of the current. Basically, we reduce the slope of the current waveform during both states of the period. And finally, what happens if we increase the switching frequency? The switching frequency is here. So if we increase the switching frequency, we will reduce the current ripple. Let's consider again this initial situation. We have a buck converter and we want to increase the switching frequency. The result is this one. Initially, we have this period, and after the change, we have this period, which is much smaller. As a result, we reduce the peak-to-peak current ripple. But note that the slope is the same in both cases. Basically, what we do is we reduce the amount of time that we keep each state of the switching period. Basically, we reduce the switching period. Okay, so now let's go back to the initial conditions. How we know if the inductance that we require for our buck converter is this one or this one or another one? So in order to answer this question, we need a rule, and the rule is considered in this situation. Let's consider that we have this inductor current with some peak-to-peak current ripple, and the important thing is that we are evaluating this current when the load is demanding the maximum current. Okay, so the output current is the maximum value of our specifications. So the rule that we typically use is that the peak-to-peak current ripple must be between 20 and 40% of the maximum current through the load. Why we do that? Why we don't use a higher current ripple? If we consider a higher current ripple, what we increase is the maximum current. If we do that, we penalize the switches. Why? Because this current, if you remember from previous videos, that current must be driven by the switches. During state 1, this current is driven by switch A, and during state 2, this current is driven by switch B. So if we increase the current ripple, we increase the maximum current that the switches must drive. And basically that is translated into higher cost of those switches and in general a higher size of those of those devices. So this is something that we don't know, and that's why we put that rule. Well, in order to determine the inductance that we need, once we know the peak-to-peak current that we want, is very easy. We have to use the general expression or the previous expression that we obtained and express the inductance as a function of the current ripple. So we use this expression where the peak-to-peak current ripple is a value that is between 20 and 40% the maximum output current. Very easy. Well, second question that we need to solve. At the beginning of the video, we say that here I have 100 microhenries, and here I also have 100 microhenries. My question is, or the question was, why the size is so different? In order to answer that question, we need to take into account that, in general, the size of an inductor is proportional to the maximum amount of energy the inductor is able to store. So I will put it in that way. The maximum energy that an inductor is able to store is 1 over the inductance, 1 over 2 times inductance times the maximum current the inductor is able to drive, to the power of 2. So in this way, if my inductor is able to drive more current, is able to store more energy. So in our buck converter, as we see in the inductor current, the inductor is storing and releasing energy. In state number 1, the amount of stored energy rises because the current rises. In state number 2, the stored energy falls because the amount of current falls. So basically what we need is an inductor able to drive this current, or in other words, we need an inductor able to store the amount of energy related to this current. Okay, so basically the answer is this inductance is the same that we have here, but this inductor is able to drive more current, or in other words, is able to store more energy. That's why the size is much higher here. So with this, we finish with the target or the scope of this video. We have seen or we have studied the current waveform we have in the inductor of a buck converter, and well, it was useful to put a rule to choose the inductance that we need, and also we talk about how that inductor current determines the size of the inductor. So as I said in previous videos, we have a lot of questions to answer in order to try to build a real buck converter. We will talk about those points in future videos. So thank you for watching this video, and see you in a future video.